Welcome and thank you all for standing by. At this time, all participants are in a listen-only mode until the question and answer session of today's conference. And to ask a question, you may press star followed by the number 1. As a reminder, this call is being recorded. If you have any objections, you may disconnect at this point. Now I will turn the meeting over to Ken Jones. You may now begin.
Thank you very much. Good morning, everybody, and thanks for joining us to this 30-minute webinar with a Q&A session at the end. So we anticipate something like 40 minutes maximum. I'm the Business Development Manager for Consultancy Services, which is a part of Field Services in Schneider Electric. With me today is Kevin Jones, the Multi-Technology Delivery Manager, also in Consultancy Services. So just have a look at the agenda. I'm going to go through what the subject of arc flash is all about. We can talk about what happens if things go wrong. We can talk about how we can mitigate the risk against arc flash. And as I said, there's a Q&A session at the end. Just so you know, this webinar has been recorded. So for those people who want to go back and have a look at the content, it will be emailed to you, a link, and this audio recording will also be available. So some questions. What really is an arc flash? How does it affect me? And what can I do to stop the worst thing happening? And one little myth is, I thought it only affected North America. Well, you'll find out that it's now becoming to affect other parts of the world, including Europe and the UK and Ireland. So what is an arc flash? So at this point, I'll hand over to my colleague, Kevin, who will take over and take you through the main content of the presentation. Thank you.
Good morning, everybody. Just a little bit of potted history about myself, Kevin Jones. I run the consultancy team. I've been a power engineer for 30 years. So the subject we're going to discuss today is, as Ken's already highlighted, becoming more and more important, I think, for us to consider in running, operating and maintaining our power distribution systems in this country. So arc flash, what is it? Well, clearly, as you can see, hopefully from the screen in front of you, it is a massive release of energy. In fact, the arc flash classification is incident energy levels, and we talk about it in calorific values. So it's joules, basically, of energy. And that energy is released in many instances, sometimes in a controlled environment, so inside any piece of switchgear, whether it's medium voltage, low voltage, or even your domestic circuit breaker at home, has a controlled arc inside it. It's just that it's a controlled. It normally is dissipated by a series of arc chutes, which break down the arc and the energies, and normally the energy is dissipated in a safe manner. However, you can't always guarantee that because you don't know where the nature of the fault may occur in your piece of electrical equipment, which means you could have an uncontrolled release of energy, and that's classified as an arc flash. So what is it? It's associated clearly with the passage of a substantial amount of energy through air or through terminals, through insulating materials, and I know that sounds very bizarre, but anything that could possibly create a substantial rise of current. So in our world, this really is faults. Whether that's a failure of a piece of equipment, whether that's somebody unfortunately creating the fault in the first place, whether it's a breakdown of insulation on some particular piece of equipment. It could be a number of different things, but we're talking about a very, very high value of current passing. Not every electrical fault creates an arc. As I've said before, some are electrical faults which are leakage currents, which will not create sufficient energies to create the magnitude of energy that will create this arc. And the magnitude is dependent upon the fault current at that point in the distribution system. So logic tells you at main low voltage terminals on the output of transformers, the fault current is normally significant, and you tend to find in these particular instances the risk associated with working in and around that zone in a switchboard is very high because of the very nature of the fault current. By the time you get down into final subcircuits, the energy levels are considerably smaller, and therefore the level of energy is reduced. However, there's another parameter that we need to consider, because it's also dependent upon the time taken to clear that fault. A statistic I think that's defined, and it's the reason why we see RCD protection used for fire, is you only need about 300 milliamps flowing in a fault condition to create incandescence to start a fire. So even at very low values of fault current, thousands of amps, a few thousands of amps, if it's there sufficiently enough, it can create quite a significant amount of energy and arcing whilst that fault is cleared. It's also not just about main switchgear or medium voltage networks. If you think about the competencies involved in managing systems, in the majority of cases, medium voltage networks tend to be operated and maintained and switched by APs, competent people who have done an awful lot of risk-based training to understand the risks of operating that equipment. The same is true for low voltage main switchboards. It tends to be qualified engineers that are doing and working in around that environment. But if you think about in an industrial environment where you may have a control panel, that may just be an operative who one day is making cream eggs and is next asked to reset a piece of equipment in a control panel. There still could be an issue with incident energy levels and arc flash at that level. So it's not just about main heavy items of plant when we talk about arc flash. We categorize it by the incident energy level scale. So as I mentioned before, it's a measure of the energy that's likely to be present for a given period of time at that point in the network that you're working. As you can see there are very low levels of incident energy, 0 to 1.2, and they go up in magnitude to 25.1 to 40 cals per square centimetre. Now that doesn't sound a lot, but what you need to do is understand what the levels of PPE that are required to actually be present in those levels. So I'm going to make things very clear. This is a function of current and time. There are things that you can do, which we will discuss about later on in the presentation, which talks about mitigation techniques. But if you have identified levels of calorific levels of these numbers, there are certain precautions you can take to try and protect yourself by wearing the correct levels of PPE. So what can and does go wrong? Unfortunately, you do have failures. You have failures in equipment, you have maloperation of equipment, you have operator errors. And we've all seen some of the, I'm assuming, some of the horrific videos on the internet that show people being inside substations subjected to very, very high levels of incident energy and arc blasts. The problem is it's very dangerous, and it could happen at any time. So I know from my career, I've been involved in an incident once when somebody was working above a 6,300 amp air circuit breaker inside a panel. They weren't really doing anything wrong. It's just that the breaker cleared a fault whilst they were leaning over the top of it. And I'm afraid all of that energy involved in clearing that fault was dissipated into their chest. So there are questions as to say why were they working in that panel in the first place when the equipment was live. But we have to try and understand the risks associated with being anywhere near it, because it can happen at any time, as we well know with electrical faults. You can have a partial discharge breakdown, you can have a circuit breaker clearing a fault whilst the door is open. This is the unknown. And really what Arc Flash tries to do is to try and help you understand the risks associated with that. But if we look actually at the effects itself, there's an awful lot of heat generated in a very short period of time. There's an awful lot of light, so very high frequency waveforms are created, and one of the clear aftermaths of such an arc flash incident is a tanning of the skin because of the levels of UV that are present during that condition. There's also a huge pressure wave created, so there's a risk of deafness. Molten metal, these are the things that are, these are the secondary things now, which is unfortunately the vaporization of the material involved in that fault condition. We're talking about materials that could be at greater than 1,000 degrees centigrade. And depending on how close you are, you could have that heading towards you at a very, very rapid speed. There's also the release of toxic gases, plasma dust, carbon monoxide and metal oxides. It's whatever is actually in the material that's been vaporized. So it is actually a very dangerous event. And that's why a lot of the switchgear construction tries to prevent you from seeing any of that. And you've seen particularly for medium voltage switchgear, huge strides forward in the construction of the equipment to try and dissipate any internal arcing in a safe manner. That's IEC 62271. We're beginning to see equivalents in the 61439 switchboard standards, which talks about particular arc venting chimneys to try and prevent any operators from actually experiencing this. But that's in a new world. The challenge we've got is a lot of our electrical infrastructure is old and doesn't have these features built in. So we have to take that into consideration. So as we've mentioned, arc blast is a significant pressure wave. Volume we talk about, it expands to 67,000 times its mass. These are just some basic statistics. And obviously projectiles are released into the immediate area, which makes it a very dangerous event. And you're looking at an LV problem. So somebody was actually changing some fuse switches inside an LV panel. I think they changed the fuses, and when they reinserted the fuses back into the circuit, there was a problem, and it blew the door open. And clearly you can see by the dissipation of the energy how the switchboard has been affected by that. So we do face this every day when we're standing, when we're operating, when we're maintaining electrical equipment. So what about the legislation? Well, clearly we have a huge raft of legislation around safety in the workplace. We have the Electricity at Work Act, and we have a lot of health and safety guidances and guidance notes about minimizing the risk and not putting people at danger from our electrical power system. Arc flash started in the United States and Canada. There are two standards that people talk about. There's the OSHA, which is the Occupational Health and Safety America, and the National Fire Prevention Association. Those two bodies were particularly interested in arc flash, primarily because their equipment is constructed differently, and they probably don't have the level of skill of operatives as we do in this country. However, there has been a couple of prosecutions of late in 2017 from the Health and Safety Executive around the operation and switching of electrical equipment, where they have specifically mentioned arc flash potential. So this is almost like a duty of care. It's not mandatory. However, it's probably very good engineering practice to first of all understand the magnitude of the fault current at every point on your network. And the Electricity at Work Act Regulation 5 very clearly points to that. It talks about the strength and capability of the installed equipment. It's also a good idea to, if you do understand the fault level on the network, to understand how fast that fault is cleared. That is a discrimination or a fault level or a grading study. People call it many, many different things, but fundamentally it's an understanding of how your network should operate under abnormal fault conditions and how long it takes you to clear the fault. And the third aspect really, I guess, is the arc flash, because as a result of those two elements, you can calculate what the levels of energy are likely to be should you be faced with a fault at that point on the network when you're exposed to it. there may be a cover off, you may be doing some testing inside the switchgear. That's the point at which you will be exposed to that energy. So the arc flash gives you a very good indication of the amount of energy that's involved at that point and what mitigation techniques you might want to deploy to remove yourself from that risk. We are seeing a lot of US and Canadian-based global organisations mandating that their sites across the UK and Europe have an arc flash assessment done. And that's primarily because their insurance company is driving those changes. They want to understand the impact. They want to try and minimise the insurance premium payouts for workers getting injured by arc flash incidents occurring on their networks. So as I mentioned, we talked about arc flash. Most people's view is it's only applicable to North America. And actually, that's very true. The two standards that we talk about are American and Canadian standards, NFPA and OSHA. But as I've already said, we are seeing some adoption in the United Kingdom, and the Health and Safety Executive are starting to use that phraseology in some of their prosecutions of late, where they're issuing prohibition notices. So understanding the energy levels, understanding the protection on the network, and doing an arc flash assessment is a complementary way of understanding the risk at those points on your distribution network. In America, it's the law of the land. You have to do it. It is mandatory because you have to ensure that your people stood in front of the equipment are protected under abnormal conditions. And we're talking about abnormal conditions. We're talking about failures of equipment or maloperation by somebody. At least there's a level of protection that's afforded to them. So let's talk about mitigating the risks. So we've done a study. We understand the impact of the energy levels at that point. And let's be clear, on some equipment, you'll find there isn't much you can do, and you can have very, very high values of calorific energy present in the substation. So maybe the mitigation risk is don't have anybody go in there. And I've seen this myself in some substations where there is a sign to say none of this equipment should be operated with anybody inside this substation. A lot of the utility companies now, with their aging assets, don't operate equipment whilst they're stood in front of it. They use remote controls, they use lanyards. So understand the risk and remove the risk. So what we can talk about, other areas. So ensuring your electrical infrastructure is fit for purpose. So first of all, understand the risk. Understand the incident energy levels that are going to be present at that point in the network. It's not then a gut feel. I've been auditing power systems for 30 years, and sometimes I know when something's not right. We all know when something's not right if we're electrical engineers. There's a strange smell or a strange hum in the substation, a strange noise. Well, that's good, but it's not as good as understanding exactly what the energies are that you might be faced with in that substation should that equipment fail. So get that fault level assessment done. Get an evaluation of the protection scheme. Make sure the protected devices are functioning correctly and operating and are meeting their operating times. And make sure the protection and grading study is up to date. You have a much better piece of the jigsaw puzzle to understand how to manage that particular piece of switchgear in the substation. Try and reduce the fault clearance time. So this goes against discrimination and grading now. What you're interested in is for certain faults trying to get a much faster clearance time. So there may be a compromise. You may have to, if you have a particularly high risk at a substation, reduce your discrimination to make sure that substation faults are cleared in a much quicker time. Or implement protection schemes that help you whilst you're in that substation, maybe, to reduce the discrimination. So in America, one of the common practices is to have a maintenance switch. That maintenance switch selects a different set of protective device settings to ensure you have a much, much faster clearance time for faults whilst you're in the substation. So you only minimise your discrimination risk when you're in that facility in front of that equipment. And then, clearly, on the procedural side of things, you have a much better understanding of the risk once you've assessed the incident energy levels. So think about how the operatives, think about how you work with the operatives. Some companies, particularly when it comes to lower parts of the network, insist, regardless of a loss of discrimination, all their control panels are category 0, or the lowest level of incident energy, which means that they, whilst they make their operatives aware of it, don't have to have any special precautions in resetting devices or operating isolators. Once you have the information, you can make sure your processes are more robust then. You can make sure that the people are kitted up correctly to enter that zone, which could be the highest risk zone of your substations. Make systems concurrently maintainable. Take the risk away from it. Try and make systems that are N+1 so you can make isolation, so you don't have to do maintenance. And we know it happens. We know items are maintained, pieces of switchgear are maintained whilst the substation's live, particularly withdrawable. So that's an area where we need to think about two different substations having A and B supplies concurrently maintainable. I can switch one off, maintain it whilst keeping the site supplies on. Make sure my permit to work is clear. Maybe include the arc flash incident energy level ratings in the permit to work. So whoever's working in that environment knows what level of PPE they need to equip themselves to go into that area. There's lots of other things that we need to consider. The earthing arrangements on site to ensure we again try and get faster clearance times for all different fault scenarios, the mechanical design of the substation, the mechanical design of the equipment, trying to remove our risk. You know, as I mentioned before, for medium voltage switchgear, the standard talks about certain arc flash performance ratings. We talk about AFLR, arc, flash, front, lateral and rear. So no matter which zone you're stood in, you're covered, and that's an element to think about in designing new equipment. Protection types, circuit breakers, relays versus fuse. These are all very important points when you're considering upgrading your system. Have a consideration of the incident energy levels, the fault levels, and the tripping times. Internal arc protection, arc detection equipment. So there is technology now that inside a switchboard can detect light of the right spectrum and the magnitude of current coming in to determine actually I have had an arc flash internally in the bus bars. What that tends to do then is to ignore any protection timings and initiate an instantaneous trip to the protection. And another area that we're seeing quite a lot of is encapsulated bus bars at medium voltage. This is where you have an earthed screen encapsulated bus bar. Again, if there are any failures of the bus bar system, in theory the fault will be shunted to earth and should be safe for an operator. So there's quite a few other things to consider when thinking about arc flash and incident energy levels. As we said, the protection coordination. There's a whole subject matter in itself in looking at discrimination, maybe compromising it, and that's why it's very good whilst you're having the protection study done and the fault level assessment done, that simultaneously you're doing the arc flash, because it might well be you can adjust protection settings to reduce incident energy levels without impacting your discrimination. It's sort of a three-way triangle that are interlinked. So one of the things that we can also think about there, as we talked about, is remote operation, racking. So there are lots of technologies around now that if we're operating and maintaining this equipment, and I'm thinking about whether it's retrofitting new equipment into old switchboards, whether it's replacing old switchboards with new, there's a number of control functions that are available now to reduce the risk. That's the first form of mitigation, is to take the risk away by taking the personnel away from that level of incident energy. That really is the first stance. From then onwards, you've got a variety of different options to try and minimize the risk. So, as I mentioned before, there are some standard policies that people are starting to talk about now, where, depending on where you are in the power system, they're trying to define the rules of the incident energy levels. So, at a control panel, some organisations are saying we really don't want to exceed the lowest values of incident energy levels, and the level of PPE and training for that is minimal. However, there are parts of your distribution system which will be significantly higher. A good example of this, which a lot of people don't consider, is DC bus arc flash. DC arc flash is probably the worst because there is no current zero. So whenever you're working with batteries, battery strings in UPSs, it's a very important consideration, arc flash. So there's a couple of ways of looking at it. There is doing your best to minimize the risk, or setting some standards of what you expect your people to be exposed to wherever they are in your building, your process, your manufacturing facility. So we talk about PPE, and it really is, I guess, like any health and safety legislation, it's the last line of defense. You should do your best to try and mitigate and remove the risk as much as possible. All this does really is give you an indication of certain types, certain levels of PPE that you can purchase, which will offer some forms of protection. And the big phrase that's in there, burn injury should be reduced and survivable. We have to be very clear that for very, very high levels of incident energy, this may just about keep you alive. And again, there are lots of stories online and videos online, particularly in North America, where people unfortunately have been exposed to these energy levels and have been disabled for the rest of their life as a result of it. So again, when you talk about PPE, you can see the suit that's on there. That would be classified probably as a Cat 25, a Cal 25 suit, and you can see you have quite a lot of clothing, additional clothing on there to provide you with the relevant protection. The PPE itself is non-flammable material. It's made of a particular type of material that can and should withstand arc blasts, but it's, as it says there, the worker involved in this incident would have expected to receive third-degree burns over only 10 to 15% of his body. That's a survivable injury. So we're still placing ourselves at risk in even if we kit up to the highest forms of PPE. And in fact, in some instances, the energy levels, particularly at main intake substations, where the fault level is very high, and it's fed from a utility company, which typically has a 1-second clearance times, the incident energy levels are above any PPE ratings that you can buy. So we talk about the levels. So we talk about up to 1.2 cal per square centimeters. So it's an untreated long shirt, long pants or trousers, safety glasses, and hearing protection. That's basic resetting of miniature circuit breakers. That's right down in the lowest level of risk category, as far as the operatives is concerned. And as I said, a lot of companies are using that at control panel levels. Category 1, we start to go up a bit more now, so we're now to 4 cals per square centimetres. So these are recommendations really now of the PPE experts in our industry. We talk about a proper shirt now, or a jacket, a hard hat, a face shield and safety glasses, some hearing protection, and leather gloves and leather work shoes. So straight away, you know, we can see we've gone from something that is probably everyday clothing in some respects with some basic safety glasses and hearing protection to something that's a little bit more specialized. As we go up further, we get into face shields and balaclavas. And as we go even further, we need a full rated arc flash suit plus hood, plus the jacket. The more layers of clothes put on, the better effectively your ability to absorb those levels of energy. And so the categories keep going higher and higher and higher. But after 40 cals per square meter, you're really on your own. you really need to think about trying to mitigate and reduce those values of energy that's in there. So again, just some basic examples there of the types of clothing we're talking about. The trouble is, everything needs to be arc resistant, you know, we do see people where they have particular PPE gear, and they might completely overwrite the arc flash calorific rating by putting a non-standard high-vis vest over the top of it. So hairnets, employee ID cards, logos, names, any arc flash clothing really should only be washed in water, nothing else. You can't use fabric conditioner because it contains animal fats, and those animal fats reduce its ability to not be flammable. So you know, you have to take very careful, take lots of precautions around the linen of the PPE equipment. So that's really a sort of an introduction to the arc flash subject matter. So as I've said, for me, whilst it's not a piece of legislation, it's another piece of the jigsaw, along with the fault levels on the network, the protection clearance times on the network, for you to really understand the risks that you are exposing yourself and employees to at that point in the network. As I say, it's okay going forward with brand new equipment, but a lot of our equipment is 25, 30 years old. We really don't know. We're not quite sure of its condition. We're not quite sure whether it'll, how it will contain arc flashes. And therefore, if there's any doubt in any shape or form, this is a really good exercise to understand the risks and to try and mitigate any exposure to those risks at that substation level. So I'm going to hand over to Ken now, who's going to explain a little bit about how we can help.
Thank you very much, Kevin. Very informative. So, guys, you've listened to the content. You've hopefully understood some of the issues involved. It's clearly a health and safety matter. So I'm just going to talk a little bit, just one slide, on how we can help mitigate some of these risks. So the best way really to understand what you've got is to do an audit. There are companies out in the marketplace. Our differentiators, we are an OEM. We understand the equipment. So we can carry out a study, not only on our equipment, but a third party as well. And I might add that our American colleagues, because it's a statutory requirement in the United States and in North America generally, we have carried out literally tens of thousands of these audits. We do share information, we share best practice, we use the same tools and software packages to conduct these audits and model the network. So if it's something that is of concern to you and it's something you want to investigate further, please do get in touch with us. There's a general email address on there which goes into our field services inbox, and there's a telephone number that you can call. As an alternative, you can contact your local Schneider sales representative, or indeed you can come to me directly. It'll just be ken.jones with the same email at schneiderelectric.com. So that's the sort of thing that we can do from consultancy services in terms of auditing and making recommendations and independent report. In addition to that, we have a training centre which is located in Coventry. We have standard courses on electrical safety, and we can help you understand and help train your staff to the required levels. And they come away with a better understanding of what equipment you've got and what precautions they need to take in terms of working practices and PPE. So that's the last slide for me. I'd like to perhaps hand back to the operator and see if anybody's got any questions that's not perhaps been covered or you want us to go over again. So I'll hand over to the operator. Thank you.
Thank you. We will now begin the question and answer session. If you would like to ask a question, please press star followed by the number 1. Please unmute your phone and record your name slowly and clearly when prompted. Your name is required to introduce your question. And to cancel your request, you may press star followed by the number 2. A moment, please, as we wait for the questions to queue up. Again, to all the participants over the phone, you may press star followed by the number 1 to ask your questions.
Perhaps I can kick it off. It's Ken Jones here again. Question for Kevin. Can you tell us a little bit about what's involved in an audit?
Yep. So if we're undertaking the arc flash study, there's quite a lot of information that we need to collect. Whether that information is readily to hand, I'd hope to think that a current single line diagram of the network is up to date, is available to us. The cable schedules, cable sizes and lengths for the installation is available, because obviously cable impedance reduces and impacts fault levels, and also an up-to-date protection study. But if it's not, then that's a service that we can provide where we'll come in and do a full assessment. We can update the single line diagram, we can do the grading study, we can work with you. We may need your operatives to help us walk around the site to work out where the cable routes are, the cable runs, to try and produce a cable schedule. So we can, depending on what information you have, we'll determine what we'll need to do in terms of collecting information. But the basics is the information is collected, it's entered into the modelling software. The modelling software produces the arc flash levels. From that, we review the protection studies and obviously the fault level.
So Kevin, a lot of installations have generators installed. How does that affect the fault level?
So depending on the mode of operation, really, of the generator sets, if their run is what's known as island mode, so the site is either on mains or generator, you have two different fault levels. So you have a fault level under mains conditions and a fault level under generator conditions. Invariably, the fault level under generator conditions is considerably lower, but you still need to consider both scenarios. The challenge comes, unfortunately, when you have mains and generators, but you can actually parallel the two supplies together, because that has the converse effect of increasing the fault levels on the network. So you're faced with significantly higher values of incident energy because in that mode of operation, you've got both the mains and the generator feeding faults current into that particular failure on the network.
So your team, Kevin, has been doing a number of these studies now, and there's a well-known international food company, which we won't mention on the call, that you've been doing quite a number of sites. What sort of things have you been finding? What sort of challenges, sort of issues?
The majority of the issues in terms of arc flash incident energy levels is down to the age of protection and the operating time of older switchgear. That tends to be the issue. In that whilst they might be serviceable, they're quite old, they're electromechanical relays, they are much slower than today's modern protection relay types, and therefore for a given value of fault current, their clearance times are much slower, and therefore, unfortunately, I squared T equals energy, their incident energy levels are higher. So what you tend to find is, if you, as I said before, if you identify a risk, a real risk, and above 40 cals per square centimetre, you really need to think about reducing that risk. It's a case of, right, what do I need to do? Can I upgrade the switchgear? If I upgrade the switchgear, let's take the human perspective of risk out of the equation. Let's make it remote. Let's make it remote controls. So again, you can see these, because I know investment in electrical infrastructure sometimes is very difficult. You can see this as a great way of getting some investment on your power infrastructure and getting the upgrades in the right place from a safety perspective.
And sometimes those investments don't need to be a full HV. They can change the protection devices.
Yes, you change the protective devices as long as that's applicable for that particular type of equipment that's installed on the network.
Okay, thank you. So we're just going over to 10:40 now. That was the scheduled stop time. If there are no further questions from the audience, just check with you, the operator, before we draw it to a close.
At this time, we don't have any questions on queue. Sir, you may proceed.
Okay, thank you. So once again, everybody, thanks for joining. Thanks for taking the time. Hope you found it informative. Like I say, we will collate the participants who've joined, and we will email out a link to the presentation. I have been passed a message just now to say that some people have struggled to join on the audio, which might explain, hopefully, the lack of questions, but we do have a number of people who've joined on the WebEx. So thank you very much. Thanks, Kevin. Very informative. Bye for now.
Thank you, and that concludes today's conference. Thank you all for joining. You may now disconnect.